Hello everyone, welcome to my presentation. My name is Jiayuan. I'm going to talk about a power router for gridded cell placement. This is a drawing work from UT Austin and Yale University. First, motivation. So asynchronous circuits have been demonstrated with several potential benefits over its synchronous counterpart, including power consumption, elastic pipelining, etc. But its adoption is limited due to the lack of EDA support. So recently, Dali, a gridded cell placement flow, was proposed for asynchronous circuits. It used a new gridded cell approach, and because of this, a dedicated power router is needed for its power design. Let me explain what a gridded cell is. In standard cell design, small cells are expanded to standard height and lead to the waste of area. In the example of Figure 1, A and B are INF gate and NAND gate. So we can see A is actually much simpler than B, and it can be smaller. But because of the standard cell design, it has to be expanded to the same height as B and lead to some waste of area in this region. So the gridded cell wants to remove this waste of area. It's very similar to standard cell with two differences. First, the cell height is flexible and can be any integer multiple of a grid value. The grid value is the pitch of metal 1 in our experiment. The second is VDD and ground pins are not at the top or bottom edge of the cell. So C and D are the layout of the same gates as A and B. VDD and ground pins are removed here, and C is actually slightly smaller than D. So in standard cell design, they usually use a standard row placement. So when these two gates are placed in a row, these VDD and ground pins are automatically connected to the power and ground mesh to the stripe. So no extra power connection is needed. But for C and D, it's not the case. The two VDD and ground pins are removed, and the cells are also with different height. So we need a dedicated power router for this gridded cell approach, and it has to take the placement result as an input. So let's see what Dali do to do placement. Dali adopts a cluster-based placement to resolve NP-well DRC violations. And figure A shows the placement result after global placement. So, but there are a lot of NP-well violations. So, and then Dali used a cluster-based approach that first divides the placement region into column subregions. In this example, there are 3 columns, and within each column, cells are grouped into mini rows. Here, each mini row is very similar to a standard row in standard cell design. And because of this mini row approach, it's able to remove all the NP-well violations, and a dedicated power router is needed. So let's compare the standard cell approach versus the gridded cell approach. In standard cell, you usually use a row-based placement, and VDD and ground mesh are generated in floor planning before placement. So when the cells are placed in a row, the VDD and ground pins are auto-connected. This shows the screenshot of standard cell placement and its power design. For gridded cell, it uses a cluster-based placement, and the power connection must be generated after placement because it needs to be adaptive to the cluster, and it needs an extra step to connect the VDD pins to the mesh, like the one shown on the right. So in our power router, for gridded cell, it has two steps. First, a power mesh generation to generate the VDD and ground mesh adaptive to the placement. So figure C shows the power mesh generation adaptive to the cluster. And detailed power routing to connect the VDD and ground pins to the closest mesh. In power mesh generation, we first read the cluster information from placement, and then generate a chip height vertical mesh. This contains both VDD and ground. These are the vertical mesh, and it's between the columns. And second, it generates a column width horizontal mesh. This alternates between VDD and ground. These are the horizontal mesh between mini rows. So this makes each mini row very similar to the standard row. And in this mesh generation, we are able to avoid all the DRCs and short violations. Figure 2 shows an example. This is the connection between the horizontal and vertical mesh. So suppose a left horizontal wire wants to connect to the right vertical wire, and the right one wants to connect to the left. There will be a collision here. So we have to detour one of them to avoid the DRC. So we are able to generate DRC-clean solutions for the mesh. And finally, we place white high-layer stripes to reduce the IR drop. In this example, this will be horizontal high-layer stripes to connect all the vertical mesh here to reduce the IR drop, similar to standard cell design. The second step, detailed power routing. We first find the closest grid point from the pin to the mesh, and then use power routing to connect the pin to the mesh. We don't need a maze routing because the routing space is empty, so pattern routing is enough. And we try the lowest metal first, and if no solutions are found, we'll try higher layers. Again, we are able to generate DRC-clean solutions. There are two major violations we are facing. The first is a spacing violation between the wire we're going to place and other pins in the same cell. The second is the min area violation when using higher layers. So this shows the flow including Dali plus power router. A shows the global placement result, and B is the clustering-based placement that generates mini rows for the cells. And because of the cluster-based placement, power mesh generation is needed. And because of the pins are not at the top or bottom edge of the cell, a special detailed power routing is needed to connect the pins to the mesh. Finally, let me show the experimental result. Our power router's inputs are left def and cluster information files. The output is def. To validate the correctness, we ran a commercial detail router for signal nets after power routing. We then use a commercial DRC sign-off tool to verify it is DRC-clean. We finally tape out a asynchronous microprocessor with this flow in a 65 nanometer process. This shows a screenshot of a chip. So A is a local view and B is a global view. In the local view, these red vertical wires are the vertical mesh, and yellow horizontal wires are the horizontal mesh. The short green wires are the result of the detailed power routing to connect the pins to the mesh. There are two white VDD and ground wires here. These are the white high layer wires that connects all the vertical mesh to reduce the IR drop. Let's compare the standard cell approach versus a gridded cell approach. We compare the end-to-end flow, Dali plus power router with the standard cell approach. So in the result, it's normalized to the standard cell approach, and lower is better here. So if you look at the die area, so the gridded cell approach can save 15% less die area due to the flexible gridded cell approach, gridded cell height. And if you look at the wire length and wire length without power routing, so this shows that power routing makes the signal nets use 2% more wire length because the power routing takes some routing space that the signal nets should be used. Finally, let me show the runtime. So this shows the result, the runtime result on synthetic benchmarks, the global placement, localization, wire localization, and power routing. So the result shows that the power routing is very fast. It takes about only 5% of the total runtime of the flow. Let me conclude my presentation. We present an open source power router for gridded cell placement flow. It contains two steps, power mesh generation and a detailed power routing. We are able to generate a DRC-clean solutions. So please visit our GitHub repository if you are interested in the project. Thank you.